If the universe were a colossal mirror, which side of the reflection would we be standing on? Those shimmering stars might be nothing more than the gentle smile of another reality, quiet and discreet, whispering behind an invisible pane. This video promises to guide you toward a question that shakes the foundations of perception. What if the world we touch, see, and believe in is only half of the story? Leave a comment and tell me how this idea makes you feel, because sometimes truth awakens through dialogue. And now, let us take the next step together. Are we only seeing half of the universe? What if the universe you trust with your eyes is only the bright half of something larger? What if reality is not a whole landscape, but a shoreline, and we have mistaken the ocean's surface for the ocean itself? When we ask whether we are only seeing half of the universe, we are not asking a childish question. We are asking the oldest question in science, and perhaps the oldest question in the human heart. What is truly out there, and what is merely the limit of our senses? Albert Einstein once warned, reality is merely an illusion, albeit a very persistent one. Bye-bye their sand. Carl Sagan offered a gentler version of the same humility when he reminded us, somewhere, something incredible is waiting to be known. Thanks for watching. And Stephen Hawking, with his calm defiance, put it plainly, look up at the stars and not down at your feet. Because of the read it severity. Taken together, these are not just inspirational lines. They are signposts pointing to a single truth. The cosmos is bigger than the stories we tell about it. So let us begin with a question that hooks the mind the way gravity hooks a wandering comet. If you could zoom out far enough, would you discover that everything you call the universe is only the illuminated face of a deeper structure, like the lit side of the moon? And if there is a shadowed side, what rules shape it? What forces sculpt it? And why can we not see it? Even in everyday life, what you see is not what is there. You do not see air, yet it presses against your skin, carries scent, shapes weather, and keeps you alive. You do not see radio waves, yet your home is saturated with them, whispering music and voices through the walls. You do not see gravity, yet it choreographs every orbit and keeps oceans loyal to the earth. In the same way, the universe may be filled with influences we do not directly perceive, yet cannot escape. Now imagine you are standing in a dark room with a single flashlight. Wherever you aim the beam, objects appear, and you feel confident you are mapping the room. But the darkness beyond the beam is not nothing. It is simply unlit. Our telescopes, our detectors, and even our theories can be like that flashlight. They illuminate a slice of the real. They do not guarantee the rest is empty. This is where the idea of the observable universe becomes both powerful and unsettling. We often speak as if the universe is what we can see, but what we can see is limited by time and speed. Light takes time to travel. The universe has an age. So our cosmic vision is trapped inside a horizon, a bubble of reachability. Beyond it may lie more galaxies, more structures, more histories, not because they are hidden by secrecy, but because the universe has not had enough time to deliver their light to us. If that feels abstract, picture yourself in the middle of a vast desert at night. Your campfire throws a circle of warmth and visibility. Inside the circle, you can count stones, read faces, tell stories. Outside the circle, the desert does not end. It simply begins to exceed your instruments. Our best observatories are cosmic campfires. They carve a circle of knowledge into an unending dark. And then we meet the second lesson, deeper and stranger. Even within the circle we can observe, most of what exists does not shine. The stars, the glowing nebulae, the galaxies painted in Hubble's colors, these are only the luminous punctuation marks. The sentence itself may be written in invisible ink. For decades, astronomers have faced an uncomfortable accounting problem. When we measure how galaxies rotate, they move as if there is more gravity than we can explain with visible matter. When we map large-scale structure, the scaffolding seems heavier than the light suggests. Something unseen appears to contribute mass and gravitational pull. Here, you can almost hear the universe teasing us. It is as if the cosmos is saying, "You may admire the lanterns, but the city is larger than the lights." This is why the phrase dark matter has such mythic power. Not because it is mystical, but because it names our ignorance in a disciplined way. We see the effect. We do not see the cause. A simple example makes it vivid. Imagine a merry-go-round spinning in a park. You stand at a distance and only see the outer horses. But when you calculate the speed needed to keep them from flying off, your math insists there must be a strong central support you cannot see, perhaps hidden beneath a decorative cover. The unseen support is not fantasy. It is demanded by motion. In the same way, galactic motion demands hidden mass. Now, does that mean the universe has a literal mirror twin? Not necessarily. But it does mean we must remain open to the possibility that what we call reality is incomplete. Because science at its best is not certainty. Science is disciplined doubt. And that brings us to your central hook. What if the hidden half is not merely extra matter scattered invisibly through our space? What if the hidden half is a deeper symmetry, like a reflection behind the glass? A second face of the cosmos that balances the first. A partner universe, not next door like a neighboring country, but coexisting in a way that makes our language stumble. Think about mirrors for a moment. A mirror does not create a new world, yet it shows a world that is real in a different sense. The reflection is tied to you, shaped by you, inseparable from your presence, and still you cannot step into it. It looks like space, but it is a boundary. It looks like a continuation, but it is an inversion. When you raise your right hand, the reflection raises its left. The physics is the same. The orientation is reversed. The mirror teaches a profound lesson. Symmetry can exist without direct contact. In modern physics, symmetry is not decoration. Symmetry is a clue to hidden structure. Many of the deepest laws we know are written in symmetries. Particles come in families. Forces have patterns. Equations behave beautifully when transformed. And sometimes, symmetry suggests that what we see is one solution among two. This is where we can weave in Hawking's legacy without turning it into myth. Hawking's most famous insight about black holes is that they are not entirely black. At the edge of a black hole, quantum effects imply a faint leakage, a whisper of radiation. This idea forces us to take seriously something that feels impossible. The vacuum is not empty. The nothing between stars is alive with fluctuations, like a quiet sea covered in ripples too small to see. If that is true, then our everyday instincts about emptiness are wrong. And once your instincts are wrong about emptiness, you become vulnerable to a much larger revelation. Perhaps the universe contains whole categories of existence that remain unlit, not because they are supernatural, but because they do not couple strongly to light. Here is a gentle analogy. Imagine a choir singing behind a thick wall. You cannot hear the words clearly, but you can feel the vibration through the floor. You know there is music because your bones register rhythm. In the same way, we might not see a hidden sector of reality, yet still feel its gravitational vibration. We might not detect it with telescopes, yet detect it with motion, structure, or subtle imprints in cosmic patterns. And now we arrive at the emotional center of this idea, the reason it holds people's attention, because it invites a kind of cosmic humility. Not the humility that shrinks you, the humility that expands you. If you are only seeing half, then wonder is not a weakness. Wonder is an accurate response. So, let us ask the question again, but with more precision and more poetry. Do we truly understand the universe, or have we mistaken the part that glows for the whole that exists? Is the observed cosmos the entire story, or merely the bright face of a deeper symmetry? Could the universe behave like a mirror, with two sides that balance each other, one visible and one hidden? And if what we call reality is only half the story, what is the other half doing, right now, while you listen? To keep this grounded, consider how often humanity has repeated the same mistake. We once thought the Earth was the center. Then we learned we orbit the Sunday. We once thought the Milky Way was the whole universe. Then we learned the sky is crowded with galaxies. We once believed atoms were solid little marbles. Then we learned they are mostly empty space held by invisible fields. Each time, the universe did not change. Our window did. There is an educational value here that is quietly life-changing. Your perception is not the judge of reality. It is a tool with a range, and the mature mind learns to respect range. A fish does not doubt the existence of mountains because it has never seen one. It simply lives within water. We, too, live within a medium of limitations, light-based senses, human-scale intuitions, and instruments that are brilliant but finite. So what do we do with this? We do what the best scientists have always done. We build bridges from what we can measure to what we can infer. We take the shadows seriously without worshiping them. We accept uncertainty without surrendering to confusion. And this is where your video can make a promise that feels honest and irresistible. We are not here to sell a fantasy. We are here to explore a possibility. We are here to walk right up to the edge of what can be known and listen for the faintest echo of what lies beyond. If you have ever stared at the night sky and felt both comforted and unsettled, this is why. The sky does not only show you objects, it shows you your limits. It is a soft mirror held above the human mind, reflecting our curiosity back at us. So let me invite you into the conversation, not as a passive viewer, but as a fellow explorer. Do you think we are only seeing half of the universe? Do you suspect that the unseen is merely more of the same, or something fundamentally different, like a mirror partner with its own rules? Write your answer in the comments in one sentence, as if you were leaving a message in a bottle for someone living on the other side of the cosmic glass. Because the most powerful ideas in science often begin as questions shared aloud. And now, with that question burning gently in the mind, we can step into the next part of the journey. Because if we truly might be seeing only half, then we must ask what form the other half could take, and what signs it might leave in the only universe our instruments can touch. So let us move forward, carefully, beautifully, and with courage, into the possibility that our universe is not alone, but paired, balanced, and stranger than light can show. What if the universe you trust with your eyes, your instruments, your mathematics, is only the bright face of a coin, and somewhere, pressed against it like breath on cold glass, there is a second face you cannot see? That question is the doorway, and it feels like stepping into a cathedral built from silence, where every star becomes a candle, and every gap between galaxies becomes a whisper. Because the idea of a twin universe, a mirror universe, is not merely science fiction with shiny costumes and dramatic portals. It is a serious kind of wonder, a possibility born from symmetry, from conservation laws, from the strange habits of quantum fields, and from the uncomfortable truth that nature often balances its books in ways we do not expect. Stephen Hawking once warned us, reality is not only stranger than we imagine, it is stranger than we can imagine. Okay, so metastated as Ox, if that is true, then a hidden cosmic counterpart is not an absurd fantasy. It is the kind of strangeness physics keeps running into, like a hand meeting a wall in the dark. And Richard Feynman gave an even sharper reminder. I think I can safely say that nobody understands quantum mechanics. Shaded 524. Between those two statements, the mind has room to breathe and to admit that the cosmos may contain structures that do not show up in ordinary intuition. Now, when people hear another universe, they often picture the popular multiverse of movies, a branching tree of timelines, a place where another you made different choices, wears different clothes, lives a slightly different life. But the mirror universe idea is not that kind of story. It is not primarily about countless alternative histories. It is about a deep mathematical pairing, a symmetry that might require two cosmic halves, not to create drama, but to preserve balance. To understand why anyone would even consider this, start with something simple and almost gentle. The habit physics has of keeping totals consistent. Energy is not supposed to appear from nowhere, and in many ways, modern cosmology has been haunted by a question that sounds philosophical but behaves like a scientific thorn. Why is there something rather than nothing? One daring answer, not a final answer, but an instructive one, is that the total might be closer to nothing than it looks. That what we call something, the galaxies, the radiation, the matter, the motion, might be compensated by an opposite accounting elsewhere, perhaps even within the structure of space-time itself. Here is where the mirror idea starts to feel less like a fairy tale and more like a geometric shadow. Imagine you are looking at a perfect lake at night, and the moon hangs above it. You see two moons, one in the sky, one in the water. The reflection is not a second moon, yet it is real in the sense that it carries information, shape, brightness, position. Now imagine a stranger kind of reflection, one that is not made of light on water, but of reality on reality. A reflection that does not simply duplicate appearances, but inverts the signs in the equations, positive to negative, forward to backward, attraction to repulsion, order increasing to order decreasing, while still obeying a coherent set of laws from its own internal perspective. If that sounds too abstract, bring it closer. Think of matter and antimatter. In particle physics, for many particles there exists an antiparticle, a partner with opposite charge. When they meet, they can annihilate into radiation, as if the universe briefly admitted that opposites can cancel, and that cancellation itself can be a kind of transformation. The mirror universe hypothesis borrows the emotional logic of that pairing, but aims it at the whole cosmos. Not countless universes, but one twin, one counterweight, one other half born at the same beginning. And yes, the beginning matters here, because the Big Bang is not just a starting gun, it is a boundary condition, a strange seam in the story where the rules we trust begin to blur. When cosmologists talk about a twin universe, they often speak as if the Big Bang could have been a symmetry event, a splitting of a single primordial quantum state into two complementary evolutions. Two universes, back to back, like two films projected from the same reel, one running forward, one running in the opposite direction. To each audience inside each theater, their own film feels like the only film, and the only direction time could possibly take. Here we touch the idea that makes people pause, the arrow of time. We live as if time only moves one way, past to future, memory to anticipation, ashes never reassemble into logs, spilled milk never climbs back into the glass. Modern physics often links this arrow to entropy, the tendency for disorder to increase, for energy to spread out, for differences to flatten. But nothing in the deepest equations of fundamental physics is obviously stamped with past and future the way our feelings are. So, some theorists ask, could the Big Bang have created two entropic stories, one in which entropy increases as we experience it, and another in which entropy increases in the opposite temporal direction? From our viewpoint, that other cosmos would look like it is running backward, but from inside it, it would look like normal life, normal causality, normal forwardness. This is not a claim that we have observed such a universe. It is a conceptual instrument, a way to test how far symmetry might reach. Einstein's name inevitably appears here, not because he wrote down the mirror universe as a finished idea, but because he trained generations of thinkers to treat reality as geometry. And he left us a sentence that functions like a lantern. The most incomprehensible thing about the universe is that it is comprehensible. Woodmaber, if the universe loves comprehension, it also loves surprise. And symmetry is one of its favorite ways to hide surprise in plain sight. Now let us connect this to something more physical, something you can picture without a chalkboard. Think about the concept of a black hole horizon. A black hole is not simply an object. It is a region of space-time from which light cannot escape. The horizon is a boundary, and boundaries in physics are where the strangest bookkeeping happens. Near that boundary, quantum field theory suggests that the vacuum is not empty. It seethes with fluctuations, pairs of virtual particles popping into existence and vanishing again. In the common telling, one member of such a pair can fall inward while the other escapes, and to an outside observer, the escape looks like radiation, Hawking radiation. The black hole loses mass, as if it slowly evaporates. The educational value here is not just the story of black holes, it is what the story teaches about the vacuum. It teaches that nothing is not a simple absence, and that energy accounting can involve negative contributions in certain contexts, even if those contributions are subtle, constrained, and difficult to isolate. This is one reason mirror concepts persist, because they resonate with the broader lesson of modern physics, that the universe is not built from solid things alone, but from fields, symmetries, and constraints. So, when someone asks, is a mirror universe just sci-fi? The most honest answer is that it depends on what you mean. If you mean a universe you can step into through a glowing doorway, then no, physics does not give you that kind of convenience. If you mean a mathematically motivated counterpart that emerges from symmetry principles, from attempts to resolve deep puzzles about time, vacuum energy, and cosmic initial conditions, then it belongs to the serious edge of theoretical exploration. It is not established fact, but it is not mere fiction either. It is a hypothesis shaped like a question, and good science is often a question sharpened into predictions. Let us make it even more visual. Imagine you hold a glove in your hand, a right glove. No matter how you rotate it in ordinary three-dimensional space, it will not become a left glove. To turn it into its mirror counterpart, you would need a kind of reflection operation, or a higher dimensional maneuver, or a transformation that changes handedness itself. Now scale that intuition up. Our universe may have a kind of handedness in its fundamental laws. Subtle asymmetries, choices of direction, choices of sign. A mirror universe would be the left glove to our right glove, not a copy, but a complementary form that restores a deeper symmetry when both are considered together. And why would nature care about restoring symmetry? Because symmetry is not decoration in physics. It is a generator of conservation laws. This is one of the most profound educational insights you can give an audience, that in modern theoretical physics, symmetry and conservation are intimately linked. When a system is symmetric under certain transformations, it tends to preserve certain quantities. That is not poetry, it is structure. So the temptation arises. If the cosmos at birth demanded a total balance, perhaps the most elegant way to achieve it was to create two halves, each carrying opposite contributions to the total. That brings us back to the question you began with. Could there exist a twin universe invisible to us, coexisting not beside us in the way a neighboring galaxy coexists, but coexisting as an opposite solution to the same originating condition? If so, the next question becomes, could it leave fingerprints? Here the examples become the bridge between wonder and testability. Consider dark matter, the unseen mass inferred from gravitational effects in galaxies and clusters. We do not see it shining, yet we see its pull in the way stars orbit, in the way galaxies spin without flying apart. Some speculative models ask whether what we call dark matter could be a gravitational influence from a hidden sector, a realm that does not interact with light the way our matter does. A mirror universe is one imaginative version of that hidden sector, not proven, but conceptually aligned with the idea that gravity might be the one messenger that leaks across boundaries other forces cannot cross. Consider dark energy, the observed acceleration of cosmic expansion. We measure the stretching of space and infer a kind of repulsive effect at the largest scales. A mirror framework could suggest a relational origin, two cosmic halves separating, or a deeper vacuum structure shaped by symmetry. Again, not confirmed, but it provides a narrative map for why the universe's large-scale behavior might be tied to something we cannot see directly. Consider the cosmic microwave background, the ancient afterglow of the early universe. It is a kind of baby picture of the cosmos, filled with tiny temperature variations that encode primordial conditions. If there were a symmetry event at the beginning, some theorists wonder whether it could leave subtle statistical patterns, odd alignments, unexpected anomalies. These are the kinds of places where a hypothesis stops being pure philosophy and starts asking to be checked. And finally, consider gravitational waves, ripples in space-time produced by massive accelerating objects, black hole mergers, neutron-star collisions. We now have instruments that can listen to space-time itself. If there were interactions across a cosmic boundary, or resonance between sectors, one could imagine signatures that look unusual, signals that do not fit the catalog of ordinary astrophysical events. This is not a promise, it is an invitation to the future, because science advances not by believing in beauty, but by building the tools to interrogate it. So the real educational heart of this topic is not that a mirror universe exists. It is what the idea teaches us about how physics thinks. It teaches us that our everyday categories, visible and invisible, real and unreal, positive and negative, are sometimes provincial. It teaches us that the vacuum is active, that time may be a local experience tied to entropy, that symmetry can act like a hidden architect, and that the largest questions often begin as the simplest ones. Why? And that is why the twin universe idea has such persuasive power in storytelling. It takes the audience's intuition, the mirror on the bathroom wall, the reflection in a window at night, the way your face appears doubled in dark glass, and then it gently turns that intuition into a cosmic metaphor that mathematics can actually touch. Not to claim certainty, but to expand the mind's comfort zone. If the universe is a mirror, then perhaps we are not alone, not in the childish sense of aliens hiding behind planets, but in the profound sense that reality itself may be paired. And if reality is paired, then maybe the Big Bang was not a solitary shout into emptiness, but a balanced chord struck across two strings, one bright, one dark, one with energy we call positive, one with a sign we would call negative, each necessary for the harmony of the whole. Which brings us naturally to the next step in the journey, because once you accept even the possibility of a mirror, you cannot help asking the most unsettling question of all, not what exists out there, but what we are missing right here. So now we move forward, slowly, carefully, into the central tension that frames everything. Why does the name Stephen Hawking keep returning whenever we whisper about a mirror universe? As if his voice were still leaning over the edge of a black hole, listening for an answer that light itself cannot carry. Because Hawking did not approach the cosmos like a poet who wants comfort, he approached it like a mathematician who refuses to blink. And the place he chose to stare was the darkest boundary nature has ever drawn, the event horizon. In everyday life, a horizon is where the sea meets the sky, a soft line that moves away as you walk toward it, always promising a beyond you cannot reach. A black hole horizon is crueler. It is not just a line on the landscape. It is a one-way seam in reality, a point where the universe says, "From here, information does not come back." And yet Hawking asked a question that sounds almost childlike, and that is why it is so dangerous. What really happens at the edge? At first glance, black holes seem like perfect prisons, pure gravity, pure silence, pure disappearance. But Hawking suspected the silence was an illusion created by our distance, a silence like snowfall that looks still until you stand close enough to hear it hiss. He took the two great languages of modern physics, general relativity and quantum mechanics, and forced them to speak in the same room. Relativity describes space-time as a smooth fabric, curving under mass, while quantum theory says the fabric is never truly calm. Even empty space trembles with restless possibility. Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics." Thanks for watching. That line lands like a small laugh, but it hides a warning, because quantum physics is not built to reassure your intuition. It is built to describe what reality does when no one is watching. And Hawking realized that if the quantum world is strange anywhere, it will be strangest where gravity is strongest, at the lip of a black hole. So he explored the vacuum near the horizon, and he treated it the way quantum theory demands, not as nothing, but as a seething field that can briefly produce pairs of particles. You can imagine it like bubbles forming on the surface of boiling water, appearing, splitting, vanishing, so quickly you cannot point to any single bubble and claim it truly existed in the ordinary sense. Most of the time, these particle pairs annihilate each other instantly, leaving no trace. But near an event horizon, the geometry of space-time itself can pull the pair apart, like a river that suddenly forks, dragging one leaf downstream while the other catches in an eddy. Here is the key image to hold in your mind. A cliff edge in the dark, with wind whipping across it. On one side is the outside universe, where we can still send signals and receive them. On the other side is the inside, where every path points deeper in. Now imagine a pair of quantum sparks appearing right at the edge. One falls inward, the other escapes outward. To the distant observer, it looks as though the black hole has emitted something, a faint warmth, a slow leak of energy. This is Hawking radiation, and it is one of the most unsettling ideas in physics because it means black holes are not eternal. They can lose mass, they can evaporate, they can die, not with a scream, but with a whisper stretched across unimaginable time. Hawking himself captured the emotional weight of this style of discovery when he said, "Remember to look up at the stars and not down at your feet." Thanks for watching. It sounds like inspiration, but in this context it becomes instruction, because the stars are where the laws reveal their hidden clauses. Now we reach the part that matters for your story, because Hawking radiation is not only about heat, it is also about accounting. Physics hates unpaid debts. If energy appears to come out of a black hole, then energy must be balanced in the books. In the simplified picture, the particle that escapes carries positive energy away, and the particle that falls in is treated as carrying negative energy relative to the outside. This is not a moral label, not good and evil, but a sign in an equation that makes the conservation laws hold steady. And that sign, that tiny minus mark, is the match that lights the forest of speculation. Because once you accept that negative energy is not just an abstract ghost, but something that can influence real outcomes in real space-time, the imagination begins to ask larger questions. If negative energy can exist locally, in these extreme quantum conditions, could it exist in a broader, more coherent way? Could it be more than a fleeting bookkeeping trick at the horizon? Could it be an entire sector of reality that we do not see? Albert Einstein once wrote, "The most incomprehensible thing about the universe is that it is comprehensible." And, end quote. Hawking's work is a demonstration of that strange gift, because from the incomprehensible violence of a black hole, he extracted a comprehensible prediction. But the same gift cuts both ways, because comprehensibility invites extension, and extension invites hypotheses like the mirror universe. So why is Hawking directly connected to the twin universe idea? Not because he declared, "There is another universe, and here is its address," but because his work changed what we are allowed to consider plausible. Before Hawking, a black hole was a final punctuation mark. Matter falls in, the story ends. After Hawking, the punctuation becomes a comma. The story continues in a different form, and the boundary becomes a translator between the classical and the quantum. And once a boundary becomes a translator, you begin to wonder what else it might translate. What else might stand on the other side, quietly balanced against everything we call real. To make this easier to picture, think of a perfectly symmetrical scale in a dark room. On the left pan, you place every star, every photon, every atom, every heartbeat of energy in our cosmos. The scale dips, heavy with positive content. Now ask, what would it take for the total to sum to zero? For the universe to be, in some deep sense, a self-canceling creation? One possible answer is that there is an equal and opposite contribution, a counterpart that we do not directly observe. Not a second universe in the science fiction sense of alternate choices and alternate you, but a second half in the symmetry sense, a cosmic reflection that makes the ledger balance. This is where people sometimes confuse the idea and imagine a mirror world where light travels at negative speed, or where time literally runs backward like a rewound film. But the more careful versions of the hypothesis are subtler. They suggest that the underlying equations could permit a mirrored solution, with opposite signs for certain quantities, while each side experiences its own reality as forward, normal, self-consistent. Like two melodies played in counterpoint, each one makes sense alone, but together they complete a harmony you could not hear from a single line. And here is the educational value that matters, because this is not just a spooky story, it is a guided tour of how science actually grows. A big idea does not begin as a belief. It begins as a pressure, a mismatch, a place where our best theories do not quite agree. Relativity and quantum mechanics are both extraordinarily successful, but they do not naturally fit together. Black holes are where they collide. Hawking radiation is one of the rare bridges we have built over that collision. So when you ask, is the mirror universe philosophical speculation or serious mathematics? The honest answer is, it depends on the model. The mood can feel philosophical, but the doorway is mathematical, because it opens from the demand that the equations remain consistent under extreme conditions. A helpful everyday analogy is this. Imagine you are listening to a distant radio station at night. Most of what you hear is the song you tuned in for, but under it there is static, and sometimes, very faintly, another station bleeds through. You cannot see the other broadcast tower. You cannot drive to it by following the sound, but the interference tells you it exists. In cosmology, we live inside our station, our observable universe, and we listen for interference in the form of anomalies, odd patterns in the cosmic microwave background, unexpected behaviors in gravity, unexplained components like dark matter and dark energy. None of these are proof of a twin universe, but they are the kinds of places where a deeper symmetry might leave fingerprints. And Hawking matters here because he trained our minds to accept that the most dramatic truths can be whispered rather than shouted. A black hole evaporating is not something you watch like fireworks. It is something you infer from a delicate argument about fields and horizons. That is the spirit of the twin universe idea, the created vacuum, if it exists. It may not announce itself with a portal in the sky. It may only reveal itself through subtle imbalances, through the way the cosmic scale refuses to settle unless you include an unseen counterweight. Hawking also leaves us with a discipline of humility, and he expressed it in a line that feels almost meditative. The universe doesn't allow perfection. Item number 7. Whether or not you take that quote in its strict context, the lesson is useful because it reminds us that nature often hides her order inside apparent disorder. A mirror universe would be exactly that kind of hidden order, not a fantasy layered on top of physics, but a symmetry that was there all along, waiting for the right questions, the right instruments, and the right patience. So when we ask, where did Hawking's black hole work lead him? It led him to a threshold, a place where the vacuum is not empty, where nothing has texture, where signs and equations can become stories about whole worlds. And whether you believe the mirror universe is true or not, you can still feel the intellectual invitation it offers, because it teaches you to see physics as more than facts. It is a way of listening. Listening to the universe where it is quietest, listening where our senses fail, listening where the math becomes the lantern. And now the thread tightens naturally into the next step of the journey, because once Hawking has placed negative energy on the table, once he has shown that the vacuum can pay strange debts, we are forced to ask what negative energy really means, not as a metaphor, but as a physical concept that could reshape our cosmology. So, let us move forward, slowly, carefully, into the heart of the idea. What is negative energy, and why does it feel like the universe's hidden mirror breathing behind the glass? What if the strangest thing in the universe is not a black hole, but the possibility that nothing can briefly go below zero and still be real? In physics, we call that idea negative energy, and it sounds like a contradiction, because in everyday life, energy feels like a one-way ticket. You spend it, you burn it, you run out. So how could energy ever be negative, as if the universe owed you a refund? Here is the quiet twist. Negative energy is not usually a new kind of fuel. Infection with Riverruff. It is more often a local dip below a chosen baseline, and that baseline is the vacuum itself. In modern quantum physics, the vacuum is not an empty stage. It is a restless ocean of fields. As John Wheeler famously put it, empty space is not empty. It is the seat of the most violent physics. I would date, that single sentence is the doorway. Because once the vacuum becomes an active medium, the question is no longer, can energy be negative in absolute terms? But can energy density in a region become lower than the vacuum level we define as zero? Afterwise, if that feels slippery, picture a calm sea at midnight. The average sea level is your reference. Now, a trough passes. For a moment, that local water height is below the average, even though the ocean still exists, even though nothing magical happened. Negative energy in many real calculations is like that trough. Not the destruction of energy, but a locally lower value compared to a reference that is already alive with motion. So is negative energy real, or only ink on paper? This is where the universe stops being polite and starts being experimental. We have laboratory phenomena that behave exactly like vacuum energy can be reduced locally. And the most famous is the Casimir effect. Two uncharged metal plates placed very close together experience an attraction as if the space between them contains slightly less vacuum energy than the space outside. No hidden magnets, no trick strings, just the quantum vacuum being edited by boundaries. That does not hand you a bucket of negative energy you can carry home, but it shows the vacuum is not a fixed zero. It is more like a living number line that can be nudged, squeezed, and shaped. And this is why quantum mechanics allows it. Because quantum fields come with fluctuations, and fluctuations can be redistributed. You can lower the energy density in one region, but the universe demands you pay it back somewhere else, or sometime else. Negative energy is often the shadow cast by that accounting. A brief valley that must be balanced by a hill. A loan that must be repaid with interest. This is not philosophy. It is enforced by inequalities in quantum field theory that limit how much negative energy you can have, and for how long. The cosmos is permissive, but not reckless. Now, let us connect this to the place where every rule is tested, the edge of a black hole. Why does negative energy show up there naturally? Things action right. Because a black hole is not only a monster of gravity, it is also a machine that stretches time and reshapes what different observers call energy. Near the event horizon, space and time tilt in a way that makes the vacuum behave differently. The vacuum is still the vacuum, but it is a vacuum seen through a gravitational lens so intense that the definition of particle becomes observer-dependent. Stephen Hawking made this unforgettable with a phrase that is as playful as it is profound. Black holes ain't so black. Thanks for watching. What he meant is that black holes can emit radiation. Not by spitting matter from inside, but because the quantum vacuum near the horizon can be torn into an imbalance that escapes. The popular picture is pairs of virtual particles blinking into existence. One falls in, one gets away. That story is a useful metaphor, but the deeper truth is more elegant. Quantum fields near the horizon are distorted, and what an observer far away calls empty is not the same as what a free-falling observer calls empty. Ava, one of chord. The mismatch produces real radiation at infinity. And for energy to be conserved in that process, the black hole must lose mass. So something with effectively negative energy must cross the horizon, reducing the black hole's total energy as measured from the outside. That is the moment negative energy stops being a quirky math option and becomes the quiet engine of a cosmic consequence. The black hole shrinks. It evaporates. Time itself becomes a slow solvent. If you want an example that lands in the mind like a stone in still water, think of a bank account. A black hole is an account with an enormous balance. Hawking radiation is a steady stream of tiny withdrawals. But why do the withdrawals work without breaking the rules? Because the bookkeeping includes a deposit of negative value into the account, and that negative deposit lowers the total. From far away, you see energy flowing out as radiation. From the perspective of conservation, you also must accept that the black hole absorbed something that effectively counted as less than nothing, and so it became lighter. Now we can return to the question that makes people sit up in the dark. Could there be an entire universe made of negative energy? Could it be more than a trough in a sea? Could it be an ocean on the other side of the mirror? Here, we must be disciplined and honest. Physics has strong evidence that local negative energy densities can occur in constrained ways. Physics does not have evidence that a macroscopic stash of free negative energy exists, and it has good reasons to be suspicious, because large, uncontrolled negative energy would not just be strange, it would be destabilizing. It could permit exotic shortcuts in space-time, or runaway effects where the normal rules of balance break down. The universe seems to allow negative energy like a poet allows metaphor, carefully, briefly, with strict rhythm, and never without counterweight. Still, the educational value of the idea is enormous. It forces us to see that energy is not only about engines and explosions. It is about definitions, observers, fields, and the structure of space-time itself. It teaches that nothing is not a blank page. It is a page already humming with invisible ink. And there is also a meditative lesson hidden in the equations, even if we never say it out loud. What we call reality is partly the art of choosing a reference and then measuring departures from it. A valley exists because a horizon exists. A negative exists because a baseline exists. In that sense, negative energy is the universe reminding us that opposites are not enemies. They are partners in balance. Richard Feynman once said, "Nature's imagination is so much greater than man's." Yes, negative energy is one of those moments where you feel that imagination, not as a fantasy, but as a disciplined surprise. A controlled impossibility that turns out to be permitted, as long as the cosmos keeps its books perfectly. So when you hear negative energy, do not imagine a glowing black liquid that violates logic. Imagine instead the vacuum as a breathing fabric. Imagine boundaries shaping what is allowed to exist. Imagine gravity bending the definitions we trusted. And imagine a black hole, silent, patient, losing itself particle by particle because the vacuum at its edge can dip below the line we call zero. And if that is possible, even in narrow, guarded forms, then the next question almost asks itself. If the universe can host a less than nothing locally, what other mirrored realities might be permitted by the same deep symmetry? What other hidden halves might be stitched to ours by laws we have only begun to read? Now let us take the next step, because the moment negative energy enters the story, the mirror becomes more than a metaphor. It becomes a testable longing, and it leads us directly into the question we cannot stop asking. Are we only seeing half of the universe? What if the darkest thing in the universe is not a tomb at all, but a lantern so subtle that it only glows when you stop believing in emptiness? What if a black hole, the ultimate symbol of cosmic silence, is quietly speaking in a language made of quantum whispers? We call it an event horizon, as if it were a fence, a clean border where reality ends and nothing returns. But the truth is more unsettling, and strangely more beautiful. The event horizon is not a wall you can touch. It is a rule written into space-time, a line where escape becomes impossible, not because a door is locked, but because every possible path leads deeper in. To an astronaut falling freely, crossing that horizon might feel like nothing at all, no sudden jolt, no cosmic alarm. And yet, to the rest of the universe watching from far away, it looks like the fall slows, stretches, and fades, as if time itself hesitates to follow. That is the first lesson. Black holes do not simply bend space, they bend the meaning of now, and they do it with a calm indifference that feels almost alive. So why are black holes not completely black? Why are they not perfect prisons? Here is where the bridge appears. The bridge between elegant theory and a phenomenon that refuses to stay in the realm of imagination. Stephen Hawking looked at the edge of a black hole and dared to combine two kingdoms that normally refuse to meet: general relativity and quantum mechanics. It is hard to overstate how radical that was, because relativity describes a smooth space-time ocean, while quantum theory insists that even the calmest ocean surface is always trembling. As Richard Feynman once put it, the vacuum is not empty. And that single sentence changes everything. In quantum physics, emptiness is restless. Picture the vacuum not as a blank canvas, but as a breathing field, always creating tiny pairs of particles and antiparticles, then erasing them again almost instantly. Like foam appearing on the surface of a dark sea, bubbles that rise and pop before your eyes can focus. Normally these pairs cancel out, a brief flicker, then nothing. But near the event horizon, the story can be interrupted. The gravity is so extreme, the geometry so warped, that the pair can be torn apart like two dancers separated mid-step by a sudden storm. One falls inward, the other escapes outward, and to the outside universe, that escaping particle looks like radiation coming from the black hole itself. This is the heart of Hawking radiation, and Hawking's own words carry the shock in plain language. Black holes are not as black as they are painted. Not because they shine like stars, but because the universe cannot keep a perfect secret at the border. where time and quantum uncertainty collide. Kip Thorne captured the emotional weight of this idea when he described black holes as the most perfect macroscopic objects in the universe. And yet Hawking showed that even perfection leaks. Now comes the part that feels like a paradox wrapped in poetry. How does the black hole pay the bill for this escaping energy? Because energy cannot appear for free, not in a universe that keeps accounts. The trick is that the particle that falls in can be assigned negative energy relative to an observer at infinity. That phrase can sound like fantasy, negative energy, but it is a real feature of the mathematics describing quantum fields and curved space-time. The simplest way to picture it is not to imagine anti-electricity, but to imagine bookkeeping with a strange twist. If a positive energy particle escapes, then something on the inside must balance the ledger, and the balance can arrive as a particle with negative energy falling inward. When the black hole absorbs that negative energy, its total mass decreases. Think of a black hole as a savings account made of gravity. Enormous, ancient, sealed. Hawking's insight was that quantum physics can slip a withdrawal slip under the door. Not a dramatic robbery, not an explosion, but a slow, patient evaporation, drop by drop, over unimaginable time. The black hole loses mass. It is as if the universe refuses to allow any object to be truly eternal, no matter how absolute it seems. To make this feel real, imagine standing near a waterfall so powerful that mist forms everywhere around you. Far from the fall, the air seems calm, but near the edge, the turbulence becomes violent, and droplets that would normally fall back into the river can be flung outward into open air. The event horizon is like that edge, except the mist is quantum fluctuation, and the droplets are particles born from the vacuum. Or imagine a treadmill. You can run forward all you want, but once the belt speed passes your maximum, the direction out is no longer a direction you can actually reach. That is what the horizon does to light and matter. And Hawking radiation is what happens when quantum randomness finds a loophole at that boundary. From here, the narrative flows naturally into the deepest educational value of the topic, because Hawking radiation is not just a curious side effect, it is a pressure test for reality. It tells us that gravity is not merely a force, it is geometry. And geometry can influence what counts as a particle, what counts as emptiness, what counts as energy. It tells us that the vacuum is not nothing. It is a dynamic ingredient of the universe. And it tells us that when you push physical law to the extreme, the universe becomes less like a machine and more like a conversation between principles. Relativity insisting on smoothness, quantum theory insisting on jitter, and the black hole forcing them to speak to each other whether they want to or not. There is also a haunting implication. If black holes evaporate, what happens to the information about everything that fell in? This question is famous because it points straight at the unfinished bridge between our theories. Even if we do not resolve it today, its presence is educational in itself, because it reveals how science advances, not by claiming certainty, but by locating the fractures in our understanding and staring into them without blinking. Hawking once said, "My goal is simple. It is a complete understanding of the universe." And the event horizon is one of the sharpest edges where that goal becomes both terrifying and luminous. So what does black hole evaporation say about the structure of the universe? It suggests that the cosmos is not built from rigid categories like inside and outside, but from relationships, from boundaries defined by motion, time, and causality. It suggests that space is not a passive stage, but an active participant capable of shaping the very definition of a particle. And it hints that the universe may be fundamentally balanced in ways we do not yet fully grasp, with positive energy here, negative contributions there, a cosmic accounting system that keeps the total story consistent even when the details seem impossible. And now the tone can soften into something almost meditative, because there is a strange humility hidden in this physics. A black hole looks like domination, like the universe flexing its most brutal strength. But Hawking radiation reveals a different truth. Even the strongest grip is not absolute. Even the darkest silence contains motion. Even the most final boundary is still part of a larger, breathing reality. If you listen closely, the black hole is not a symbol of annihilation. It is a teacher of limits, and a reminder that nature often hides its most profound lessons in the places we fear to look. So let me leave you with the question that naturally opens the next step of our journey. If the edge of a black hole can turn vacuum into a whisper of light, if the darkest object can leak its existence back into the cosmos, then what else might be happening at the boundaries we cannot see, in the seams between what we call real and what we call empty? Thank you for watching. What if the Big Bang was not the universe's first breath, but the moment reality split into two matching halves, like a single note becoming a chord? For decades, we have repeated the familiar story, a beginning from nothing, a sudden ignition of space and time. But there is another way to picture it. Less like creation, more like separation. Less like a lone birth, more like a cosmic pairing. Stephen Hawking once wrote, "Because there is a law such as gravity, the universe can and will create itself from nothing." Dominus 80 Minigens. Whether you take that line as literal physics or poetic shorthand, it points toward a deeper idea, that nothing in modern cosmology is not an empty box. It is a restless stage, full of rules, full of possibility. And once you accept that possibility, a quiet question rises, like a tide under moonlight. Could the Big Bang be the splitting of a balanced whole, rather than the appearance of something from absolute emptiness? Imagine you are holding a perfectly symmetrical coin, one face bright, one face dark, but the metal is one piece. Now imagine the coin is struck, not destroyed, but separated into two coins, each carrying opposite markings, each necessary to describe the original symmetry. In that picture, our universe is not the only face. It is one face of a paired event. This is where the phrase, "the total energy of the universe could be zero," begins to feel less like a trick and more like a lesson in humility. Energy is not just the glowing kind we see in stars. It also hides in gravity, in the shape of space, in the way mass curves the cosmic fabric. A universe filled with positive energy and matter and radiation could, in principle, be balanced by negative gravitational energy, so that the grand total is not a mountain of excess, but a quiet accounting, a ledger that closes. Try this as a simple image. Picture a vast bank account. Matter and light deposit energy. Gravity withdraws it. You can be rich in stars and galaxies, and yet the balance can still read zero, because gravity is the universe's deep debt, the inward pull that pays back the outward abundance. Physicist Edward Tryon famously suggested a provocative thought, that the universe might be a kind of quantum fluctuation, because, as the idea goes, the net energy could be zero. Even if you do not follow every equation, you can still feel the intuition. A cosmos that does not borrow from outside itself, a cosmos that is its own closed circle. Now let us move one step deeper, into the heart of your theme. If the total can be zero, then the Big Bang does not have to be a magical exception. It can be an unfolding of symmetry, a transformation rather than a violation. Alan Guth described inflation as the ultimate free lunch. Thanks for watching. That line is remembered because it is bold, but it is also strangely gentle, because it hints that the universe might have paid for itself in a way we did not expect. Not with coins, but with opposites. Not with a single sign, but with plus and minus together. So we arrive at the next question, the one that feels almost forbidden to say out loud. Does every positive energy require a negative counterpart? In everyday life, we are trained to think of energy as always positive, as fuel, as heat, as light. But modern physics has long allowed something subtler. In quantum theory, the vacuum is not a dead void. It is a seething field with fluctuations, brief borrowings and repayments that happen beneath our senses. And in certain contexts, physicists speak about negative energy density, not as fantasy, but as a real feature in specific quantum situations. Here is a way to make it visual. Imagine the ocean at night. From above, it looks smooth, black, quiet. But if you dip your hand below the surface, you feel constant motion, small currents, hidden waves. The quantum vacuum is that ocean. What we call nothing is not the absence of activity. It is activity without a headline. If the Big Bang was born from such a vacuum, then it may not have been a single universe bursting out. It may have been a paired event, a symmetry unfolding into two complementary realities. Some modern proposals go even further, suggesting a kind of mirror cosmology where the Big Bang is the shared hinge, and two universes open away from it in opposite directions, each with its own arrow of time. If that sounds like science fiction, pause and notice what makes it feel that way. It is not the mathematics. It is the emotion of it. We are used to being alone in our origin story. A twin universe challenges not only our models, but our mood. And yet, physics has always advanced by asking us to surrender comforting instincts. We surrendered the idea that Earth is central. We surrendered the idea that time is universal. We surrendered the idea that space is a rigid stage. So why should we cling to the idea that the Big Bang must be a solitary beginning? Let us connect the pieces with an example you can almost see. Think of particle physics, where a high-energy collision can produce a particle and an antiparticle, two beings born together, opposite in charge, mirrored in properties, linked by conservation laws. Now scale that intuition up, not as a claim, but as a possibility. What if the Big Bang is the cosmic version of pair production, not a single thing appearing, but two complementary halves emerging together, so that the bookkeeping of reality remains balanced? This is where the educational value becomes quietly profound. Because the lesson is not only about cosmology, it is about how to think. When we ask whether the universe came from nothing, we often smuggle in an old definition of nothing, a blank emptiness with no laws. But physics invites us to refine our words, to ask, what do we mean by nothing? What do we mean by beginning? What do we mean by balance? Lawrence Krauss once phrased it sharply, that nothing is not what you think it is. Whether you agree with every implication or not, the core educational point remains, in science, words are not decorations, they are instruments. If we tune them poorly, our conclusions wobble. And in this tuning, the idea of the Big Bang as a split becomes a disciplined kind of imagination. It does not demand belief. It demands clarity. It asks you to distinguish between absolute philosophical nothingness and the physical vacuum, between a narrative beginning and a mathematical boundary, between a comfortable origin story and a testable model. Of course, there is a responsible line we must hold. These ideas are beautiful, but beauty is not proof. They remain hypotheses, ways of organizing what we know into a deeper symmetry, and then asking what new predictions might follow. That is the scientific spirit, not to declare mysteries solved, but to shape them into questions that experiments can someday touch. So as we step from wonder into rigor, notice what has happened in your mind. A moment ago, the Big Bang was a door marked start. Every 5 minutes. Now it becomes a hinge, a mirror line, a divide between two complementary accounts of reality. And if that is even remotely true, then the universe is not just expanding, it is balancing. not just moving forward, but holding opposites in a silent embrace. Not just a blaze of existence, but a meditation on symmetry. Which brings us to the next passage of our journey, the one that follows naturally from everything we have just unfolded. If the Big Bang might be a split, if the total might be zero, if plus might require minus, then we must ask the question that changes how we look at the night sky. What if the reason time feels like a one-way river is not because the river has only one direction, but because we are standing on one bank? We live inside a universe that seems to insist on a simple rule. Yesterday can be remembered. Tomorrow cannot. A candle burns down. It does not unburn. A face ages. It does not unage. So the question that quietly haunts every human life is this: why does time only flow one way? And if the cosmos is stranger than we think, could there be a place where time flows the other way? To approach that mystery without losing ourselves in poetry alone, we need a compass word that science trusts. Entropy. The word sounds cold, but it is really a story about order, about memory, about the fragile arrangements that briefly hold together before they dissolve. The physicist Ludwig Boltzmann is often linked to the modern meaning of entropy, and the heart of his message can be felt in one simple image. A neat deck of cards becomes messy after shuffling. It can become neat again. But the number of messy arrangements is so overwhelming that disorder is what you should expect. This is why entropy matters. Not because it is a gloomy law of decay, but because it explains why the universe keeps leaving fingerprints of the past behind it. A famous line from Sir Arthur Eddington captures the drama. The law that entropy always increases holds the supreme position among the laws of nature. Thanks for watching. In that sentence, you can hear the weight of the claim. If entropy tends to rise, then the universe naturally moves from rare arrangements to common ones, from ordered states to disordered states, and that trend becomes what we experience as the arrow of time. Now bring that back down to the scale of a quiet living room. You pour a drop of perfume into the air. At first, it is a small cloud, a secret. Then it spreads. It fills the space. You never see it gather itself back into a single drop. Not because physics forbids it absolutely, but because it is astronomically unlikely. The same with a cup of hot coffee left on a table. Heat drifts into the room. The cup cools. The room warms by an invisible whisper. You never watch the room donate its warmth back into the cup to reheat the coffee. These are not just household curiosities. They are entropy speaking in the language of everyday life. And this is where the philosophical electricity enters the room. If entropy is the reason the arrow of time points forward for us, then time itself may not be fundamentally one way. It may be that the deeper laws of physics do not care about past or future at all. Many of the equations work almost the same if you run them backward. What changes is not the rules. What changes is the arrangement, the boundary condition. The universe began in an extraordinarily low entropy state, a state of uncanny order, a cosmic starting pose that is so special that it still confuses physicists today. The moment you accept that, you begin to see why time feels directional, because the universe has somewhere to fall, from order into disorder, from unlikely into likely, from delicate structure into the easier sea of randomness. Stephen Hawking once put it plainly: the increase of disorder or entropy is what distinguishes the past from the future. An experience of unity. It is a clean sentence, but it hides a storm. Because if the past and future are distinguished by entropy, then the most haunting possibility is that another region of reality could distinguish them differently. Now imagine the twin universe idea. Not a fantasy multiverse where copies of you make different choices, but a mirror cosmos born alongside ours. Symmetric, complementary. If our universe began with low entropy and then entropy increased, what would it mean for a twin universe? One that is required by symmetry. Could it begin in the same low entropy condition, but evolve in the opposite direction of time relative to us? From our perspective, it would look like entropy decreasing, like shattered glass gathering itself off the floor, like smoke diving back into a cigarette, like ash reassembling into paper. Absurd. Impossible. And yet, inside that universe, it might feel as normal as our own mornings. Here is the key that many people miss. If you lived in a universe where entropy decreased toward what we call the past, you would still experience your own arrow of time as forward, because your memories would still align with the direction in which entropy increases for you locally. Memory is not mystical here. Memory is physical. A memory is an ordered pattern in a brain, a stable record in matter, a trail of correlations. And creating records generates entropy. So, whichever way your universe produces reliable records, that direction will feel like the future. This is why two opposite arrows can both be right from the inside. Each observer lives downstream of their own entropy gradient. Each calls that downstream direction forward. Let us make this vivid with a simple film thought experiment. You watch a video of an egg falling and breaking on a kitchen floor. You do not need training in physics to know the direction it is being played, because breaking increases disorder. Now play it backward. The fragments leap. They lock. The yolk climbs into its shell. The shell seals. You immediately feel that something is wrong, not because the microscopic laws have been violated in an obvious way, but because the sequence runs against the entropy gradient you expect. Your intuition is an entropy detector built by a lifetime of living in one direction. This is also why the question becomes spiritual without leaving science, because it touches the meaning of change, the meaning of loss, the meaning of becoming. We are creatures who feel time because we are made of processes that produce entropy. We are candles that know the shape of their own flame. We are wave crests that can only remember the sea behind them. Physicist Sean Carroll has a line that many people carry with them. The arrow of time is an emergent phenomenon. In a moments, and in moments, and in moments. Emergent means it is not fundamental in the way space might be, or charge, or the speed of light. It arises from the statistical behavior of enormous numbers of particles and the special initial condition of the cosmos. If that is true, then time is not a dictator. Time is a storyteller, and entropy is the grammar of its story. So, could a twin universe have the opposite grammar? Some models in cosmology play with exactly that symmetry. Two universes branching from a shared origin, each with an arrow pointing away from the beginning. For us, the beginning sits behind us. For them, the beginning sits behind them too. But when we compare notes, each calls the other backward. Each calls the other impossible, and yet each could be internally consistent. If you are wondering where education lives in all this, it lives in the discipline of separating what we know from what we imagine. We know that entropy is deeply connected to the arrow of time in our observed universe. We know that many fundamental laws are nearly time-symmetric. We know that the universe began in a remarkably low entropy state. We do not yet know why that initial condition was so special, and we do not yet know whether a mirror cosmos is real. But when a hypothesis forces us to ask sharper questions about entropy, about memory, about the beginning conditions of the universe, it is already doing the work that science is meant to do. It makes the mind more precise, and at the same time, more humble, because the final thought is this: perhaps time is not a single arrow carved into reality. Perhaps it is two arrows, or a field of arrows, or a deeper symmetry that only looks like direction when you stand inside it. And perhaps the strangest part is not that a twin universe could run the other way, but that from inside it, it would feel like home. So, let me leave you with the question that naturally opens the next step of our journey. If entropy is the reason the universe gives us a forward direction, then what does it say about the cosmos that it began with so much order? And what else might be hiding behind that first low-entropy sunrise? What if gravity is not a handshake that pulls worlds together, but a quiet breath that pushes them apart as if the universe itself can exhale? We are used to thinking of gravity as devotion, a force that gathers dust into planets, planets into solar systems, and solar systems into galaxies, like an ancient shepherd guiding luminous herds across a dark plain. But the mirror universe idea asks us to imagine the opposite, a reality where the shepherd becomes a wind, where mass does not invite, it refuses, where the presence of a star does not carve a valley in space-time, it raises a hill. Albert Einstein once gave us an image that still feels like poetry, that gravity is not a pull, but the shape of space-time itself. Space and time are not conditions in which we live, but modes by which we think, he wrote, and with that single turn of language, he reminded us that the universe is as much geometry as it is matter. So if gravity is geometry, the mirror question becomes strangely precise. What happens if the geometry flips its sign? What happens if the curvature that normally makes things fall inward instead makes them slide away? Now, a word that sounds simple but behaves like a nightmare in equations. Negative mass. Not antimatter, not a science fiction copy of atoms with different colors, but a change in the way mass responds to forces, a kind of cosmic minus sign. If ordinary mass is a stone that dents the fabric of reality, negative mass would be a stone that dents the fabric upward, a bump instead of a well. And in that world, gravity could feel like repulsion, not because the force changed its mind, but because the terrain changed shape beneath every step. To picture this, imagine a long rubber sheet, the classic classroom demonstration. Put a heavy ball in the center, and smaller balls roll toward it, their paths bending as if the sheet were whispering instructions. Now imagine the central ball is replaced with something that creates a raised dome. Release a small ball nearby, and it will roll away, not because it hates the dome, but because the slope tells it to go. Repulsive gravity, in that sense, is not an emotion, it is topography. But the next question arrives like thunder behind the first. Could negative mass be stable? Here, the story becomes both fascinating and cautionary. Many simple models of negative mass create runaway behavior. A strange chase where a negative mass and a positive mass accelerate together, one falling toward the other while the other flees, both gaining speed without an obvious fuel source. It feels like a perpetual motion machine wearing a lab coat, and physics does not tolerate free lunches. So the responsible way to tell this story is the way good science always tells it, as a possibility, as a boundary line, as a hypothesis that forces us to ask what the rules truly allow. Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics," and he meant it as a warning against false certainty. Negative energy and negative mass ideas often emerge from the quantum world, where the vacuum is not empty, and where fluctuations can briefly borrow energy in ways that sound mystical until you do the math. Stephen Hawking took this quantum restlessness and placed it at the edge of a black hole, and showed that black holes may not be eternal. They can radiate, they can lose mass, they can fade, as if even the darkest objects must eventually pay their debts to time. Hawking's work made negative energy feel less like fantasy and more like a real actor in the cosmic play. Because in the story of Hawking radiation, a negative energy contribution effectively reduces the black hole's mass. So, if negative energy can appear locally in our universe, near extreme horizons, the mind naturally wonders whether it could exist globally, as a whole cosmological sector, a mirror side. And if that mirror side exists, what kind of structures would it build? Here is where imagination becomes educational, because the best way to learn a concept is to try to live inside it. If gravity repels, then collapse is no longer the engine of structure formation. In our universe, stars form when clouds of gas cool, lose pressure support, and gravity wins, pulling material inward until the center becomes hot and dense enough to ignite fusion. That is our familiar recipe. Cooling plus attraction equals birth. But in a mirror universe with repulsive gravity, the inward pull is replaced by outward insistence. So how does anything ever gather? How does anything ever become a star? One possibility is that the mirror universe does not build stars the way we do. It builds them through confinement by other mechanisms, like pressure traps, fields, or boundary effects. Think of how in our own universe, not everything is held together by gravity alone. Atoms are held by electromagnetism, nuclei by the strong force. A mirror universe could, in principle, have different balances of forces, different signs, different effective pressures in the vacuum itself. In that case, structure might arise not from falling into wells, but from being squeezed between hills, like foam collecting in the seams between waves. A more intuitive example: imagine a landscape of many domes rather than valleys. Where do rolling marbles end up? They do not gather at the center of a dome. They gather in the low places between domes, in the saddles, in the narrow corridors where slopes cancel. In a repulsive gravity cosmos, matter might pool in between regions, forming filaments not because gravity drags it in, but because repulsion herds it into shared boundaries. The cosmic web could still exist, but its logic would be inverted, not a spider web woven by attraction, but a river network carved by avoidance. And what about galaxies? In our universe, galaxies are the long memory of gravity. They are what happens when matter has had billions of years to gather, rotate, merge, and settle into patterns. If repulsive gravity dominates, then mergers become rare, and settling becomes something else entirely. Galaxies might not be islands that pull neighbors toward them. They might be bubbles that keep neighbors away. Instead of dense spirals, you might imagine vast, diffuse structures, slowly expanding, held in shape by internal dynamics rather than external capture. Not a city of stars, but a drifting fog that still has order, a kind of negative architecture. Now the deepest part, the part that makes this more than a clever thought experiment, is that mirror universe ideas sometimes connect to puzzles we actually face. Why does the universe seem to contain so much unseen influence? Why do galaxies rotate as if extra mass is present? Why does cosmic expansion accelerate? These questions gave us the names dark matter and dark energy. Names that are honest admissions of ignorance, labels on sealed boxes. And some theorists have explored whether mirror sectors or hidden gravitational effects from other degrees of freedom could contribute to what we call dark phenomena. Not proven, not settled, but suggestive enough to keep the mind awake at night. Kip Thorne once wrote about how beauty can guide physics, not as proof, but as a compass, and that is how mirror universe ideas often feel. They are beautiful because they offer symmetry, and symmetry is one of the universe's favorite languages. But beauty is not evidence, and the mature stance is to let beauty inspire better questions, not final answers. So we return to the hook. If gravity can become repulsion in a mirror world, and if negative mass can be made stable under the right rules, then stars and galaxies might still form, but by unfamiliar pathways, like flowers blooming underwater, obeying a physics that is still physics, yet feels like a dream to us. And perhaps that is the educational gift here, because it forces us to separate the laws themselves from our habit of interpreting them. We have learned to call attraction natural, and repulsion strange, But nature is not obliged to match our instincts. In the end, the mirror universe is not merely a second cosmos. It is a mirror held up to our certainty. It asks whether the universe is a single story or a paired song, a harmony built from opposites, a balance where every plus has a hidden minus, and every bright sky may have an unseen counterpart listening from the dark. And as we step forward from this inverted physics, a final question waits like a doorway. If such a mirror world can exist without light, without direct contact, how would it ever leave fingerprints on our reality? And are we already living among those fingerprints without recognizing the hand? What if the clearest evidence for another universe is not a portal in science fiction, but a quiet mismatch in our own equations, a subtle wobble in the sky that refuses to go away? When we talk about observable traces, we are really asking a disciplined question. Can two universes interact without ever sharing light, without trading atoms, without touching in any ordinary sense, and still leave fingerprints on each other through gravity alone? Albert Einstein once warned us with a kind of gentle humility, the most incomprehensible thing about the universe is that it is comprehensible. That stated it. And yet, sometimes the universe feels comprehensible right up until it doesn't, right up until the numbers demand an extra presence we cannot see. Imagine a dark auditorium, two enormous drums separated by a thin wall. You strike one drum, and the other trembles faintly, not because sound passes through, but because the wall itself vibrates. That is the mood of modern cosmology, because gravity is not just a force, it is the flexing of the stage on which all forces perform. So the question becomes, could gravity leak across a boundary, a brain, a mirror interface, and make our universe feel heavier, faster, more accelerated than it should? This is where dark matter enters like a shadow that refuses to leave the room. We see galaxies spinning, and they spin as if they are wrapped in invisible mass. We see clusters bending light, as if a ghostly scaffolding is holding them together. Vera Rubin described the feeling with a simplicity that still stings. What you see is not what you get. Thanks for watching. If a mirror universe exists, one of the most tempting ideas is that its gravity might be the missing glue, not a new particle in our space, but a neighboring reality pressing on ours like a hand on glass. A helpful picture is this. Hold a thin sheet between your palms, press from the other side, and the sheet curves toward you. You never see the hand. You only see the shape it forces into your world. But then we take one step further, because dark energy is stranger still. Dark matter acts like extra weight. Dark energy acts like a silent push, an acceleration of expansion that makes distant galaxies flee faster and faster. Stephen Hawking once said, "The universe doesn't allow perfection." 87. If the Big Bang were not a lone beginning, but a kind of split, two halves balancing each other, then perhaps the acceleration is not an internal engine, but the aftertaste of separation, two cosmic sheets drifting apart, their geometry stretching, their relationship written as a pressure we call dark energy. In that picture, dark energy is not merely something. It is the feeling of distance increasing between twins who cannot reunite. Now, let's connect this to what we can actually measure, because poetry alone is never enough for science. Physics demands predictions, and the sky is the laboratory. So we ask, where would a mirror universe leave its most honest signature? Not in bright explosions, but in statistics, in patterns, in the leftover echoes of the beginning. Start with gravitational waves, those faint ripples in space-time that LIGO and Virgo have already heard. Kip Thorne called them messengers from the dark side of the universe, meaning not evil, but unseen, because gravitational waves pass through matter the way wind passes through a forest, disturbing leaves, not trunks. If another universe couples to ours through gravity, then in principle it could contribute to a background hum of gravitational waves, a persistent ocean of ripples with no obvious source in our own cosmic history. Think of it like standing near the sea at night. You cannot name every wave, but you can hear the whole ocean breathing. Some researchers look for that breathing, a stochastic background, and ask whether part of it might be foreign, not from our mergers, but from interactions at a boundary we cannot see. Then there is the CMB, the cosmic microwave background, the oldest light we can observe, a baby photograph of the universe when it was only hundreds of thousands of years old. It is remarkably uniform, and yet it contains tiny temperature variations, the seeds of all galaxies. Here the mirror universe idea becomes both thrilling and dangerous. Thrilling because even a small interaction near the beginning could leave a telltale asymmetry. Dangerous because the early universe is a noisy place in theory, and many different models can mimic the same small anomalies. Still, people point to oddities, cold spots, preferred directions, unexpected alignments, and ask, are these mere statistical flukes or the faint crease of a cosmic folding? A simple example, imagine two soap bubbles forming side by side. They separate, but where they once touched, the film can retain a subtle distortion, a line you can see only at the right angle. The CMB might hold such lines, if there was ever contact, or resonance, or symmetry breaking between two halves of creation. And what about neutrinos? Those nearly massless particles that pass through you in uncountable numbers each second. They are called ghost particles for a reason, because they barely interact, and that makes them tempting candidates for boundary-crossing stories. Neutrinos oscillate between flavors, they change identity as they travel, and the details of those oscillations are measured with exquisite care. If there were a mirror sector, a hidden partner reality with its own neutrinos, some models imagine tiny mixings, tiny disappearances, tiny imbalances, like a coin that occasionally falls through a crack in the floor. You do not see the crack. You only notice the missing coin. That is the flavor of the search. Not spectacle, but accounting, a cosmic audit where the smallest discrepancy becomes a doorway for imagination. But notice what is happening now. We are collecting maybes that must survive the harshest test. Could they be explained without the mirror universe at all? This is where the limits arrive, not as villains, but as guardians. Why is this hypothesis still unconfirmed? Because gravity is both powerful and frustrating. It shapes the universe, yet it is the hardest interaction to isolate cleanly. If a mirror universe influences us gravitationally, its effects could look exactly like many other things. A new particle, a tweak to general relativity, a systematic error in measurements, an overlooked bias in galaxy surveys, or simply cosmic variance. The fact that we only have one universe to measure, one sky, one sample size of one. Richard Feynman captured the discipline we need. The first principle is that you must not fool yourself. Number 5. In cosmology, fooling yourself can be as easy as mistaking a statistical coincidence for a message. There are also mathematical barriers, because our best theories still live in separate kingdoms. General relativity rules the large, quantum mechanics rules the small, and the mirror universe idea often lives precisely in the borderlands where those kingdoms clash. To model a true boundary between universes, or a brain interaction, or a symmetric creation with opposite arrows of time, you need a language that unifies gravity with quantum rules. And that language is still incomplete. Not absent, not hopeless, but unfinished, like a map drawn with coastlines but missing the mountains. And then there is the philosophical edge, not as an escape from rigor, but as a reminder of what we are doing. Where is the boundary between physics and philosophy? It is not at wonder. Wonder is allowed. It is at testability. A beautiful idea becomes science when it risks being wrong in a measurable way. So, the mirror universe must eventually offer more than atmosphere. It must offer a signature that is difficult to fake, a pattern that other explanations struggle to reproduce. Still, even before final proof, there is educational value here that is profound, because it teaches us how science actually moves, not by declaring certainty, but by building a ladder of constraints, by asking sharper questions, by turning maybe into if and only if. In Region 7 is that mathematically taughter. It teaches us to respect the invisible without worshiping it, to chase mysteries without becoming prisoners of them. So we return to the final questions, and we let them land softly, like snow settling on a silent desert. If a twin universe exists, is the universe still a single thing, or is it a paired structure? A double heartbeat, a cosmic inhale and exhale. If there is another side, do we live inside one half of a balanced equation, mistaking the half for the whole? And if our instruments are extensions of our senses, and our senses are extensions of our minds, then one more question slips in, quiet, almost meditative. Are we seeing only one side of the mirror because reality is one-sided, or because consciousness itself is positioned on a single face of the glass? Hold that thought, because the next step is not to believe, but to look more carefully at rotation curves, at lensing maps, at wave backgrounds, at the ancient texture of the CMB, and to ask, which of these whispers is merely noise, and which one is the universe trying, very gently, to tell us that we are not alone in the dark?